Another question about filters. This one is a low pass filter. It says build this circuit on Multisim. I'll build that. I've already done that in a different separate video, but I'll just quickly show you because I've done it in a different way, a little bit different. It's almost the same action, the same everything, but I'll just show you quickly. So you need to probably watch that video and this one both together to get that question answered, because this is a distinction question. I'm not going to answer everything for you. You need to do a little bit of work for yourself. So what it says is it's a low pass filter using a 1 kilo ohm resistor and 10 nanofarad capacitor. Now you need to correct that capacitor. The first assignment I sent was 3.3 nanofarad, and I sent you another amended version of the assignment which says 10 nanofarad. It has to be 10 nanofarad. It doesn't have to be, but it's just in this assignment I decided to be 10 nanofarad. Use a power supply with a 10 volt AC peak output. So this the peak voltage would be 10 volts. So if your power supply you pick is just showing you the RMS value, then you need to find out how much the RMS value would be. If the peak is 10, then RMS would be about 7 volts. Set the initial frequency to build the circuit. The initial frequency, set it at 10 Hertz, and then you keep increasing the frequency as I've given you that table, and I'll go through that in the video. All I want to show you on this board is just to show you how to calculate the cutoff frequency, because it says calculate the cutoff frequency, build the circuit, which will show you, which is already in the other video, and I'll show you again. And also it says calculate the cutoff frequency and also verify your calculated value with your measurement using a Bode plotter. And I'll show you that in the video. But what I want to show you here is the cutoff frequency calculation. There is a formula for cutoff frequency. You can say FC as in the cutoff frequency is 1 over 2 pi f c. Just get rid of that one. Cutoff frequency is FC, and the formula for it is 1 over 2 pi RC. So basically all you do is just put the values there. 1 over 2 times pi times R, in this case is 1 kilo ohm, so it's 1000 times C, 10 nanofarad, 10 times 10 to the power of minus 9. So the answer for the cutoff frequency will be 15,915 Hertz, or you could just say cutoff frequency is 15.915 kilohertz. So that's the calculation. I'll show you the rest of it on the screen. Right, for this distinction question, it just says build the circuit on Multisim. So this is already built for you. This is the circuit built on Multisim. Now it says 10 volt supply peak, 10 volt AC peak. Now your source of supply, you either choose, if you just go to the sources of supply, you can choose the value of the voltage, either the RMS or peak for for your voltage. In this case, it's just giving you the RMS. If I went to basics and pick power sources again, just to show you what I mean, there's power sources, AC supply. It comes here, right? So this is how I've dropped that one there. So this actually just comes standard RMS, right? But it says 10 volt 10 volt peak. So if you are going to build this, I would say calculate, if you don't want to change this, if you can change it like this one, I can't go actually change that to peak instead of RMS. Then what you'll do, instead of changing the voltage of the RMS of the supply, you change the value of the voltage. So 10 volt peak would be 7 volts. So 10 volt peak would be 7 volts RMS. So I would just type, let's just get rid of this one. So I would just basically double click that and say values. Instead of 10 volts, I would put down 7 volts here. And to be exact, it would be 7.07 volts, but I'll just put down 7 volts RMS, which is the same as 10 volts peak value. So that's that. This is the circuit built for you. It's a low pass filter. That means it passes or it allows the low frequencies to pass through. This is your input coming through the circuit, and it comes out of this end of the circuit to the output. And what I've done, I've connected the both channels of this oscilloscope. This is an oscilloscope, and I've connected the negative parts to the earth, and the positive side of the probes, one of them to the input, the red one. I've made it red, and I've made the color of the other channel B, in blue, so we know when the waveforms come, or when we see the waveforms for the input and output, then we can see which one is input, which one is output. And I've also connected this one, which is called Bode plotter. Where you find those is on this side. So you have oscilloscope, and then 4-channel oscilloscope, Bode plotter. And this is your Bode plotter, so I just bring it and drop it there. And we don't need that extra one. So again, negative ends of the input and outputs of the Bode plotter are connected to the earth, and the positives the same as the oscilloscope. One is the input is connected to the input, output is connected to the output. That's it, simple as that. And the value of the resistor is 1 kilo, 10 nanofarad for the capacitor. And what you do, you have to, so this is building the circuit. You can just take a screenshot of this video right here and say the circuit is built. So that's A, done. B, I did that separately on a board, so you know how to calculate the cutoff frequency. C, vary the frequency and copy and complete the table on Excel similar to the one below. So what you have to do, and then with that table, it says D, plot the graph of voltage against frequency on Excel to determine the cutoff frequency. And then E and F is explanations, briefly describe how the calculated and graphical cutoff frequency compare. And then F, explain the operation of the low pass filter and show how varying circuit resistor and capacitor values affect the filter's response. So how basically, if you change the values of the resistor or change the values of the capacitor, how it would affect the circuit. This is a distinction question, so I'm not getting into too much of that end of the question. All I'm trying to do is to make it simple for you, because you haven't got the software to do this. So the software is now there. I've made it for you, so you just take a screenshot of this and explain how you've made it. And also for the frequency for the making the table. What I've done, basically, I've got there and put the values there, kept changing, make a table, open an Excel sheet like this, and just go to column 1 and just type down here frequency, just the same as that example is given you in the question, and just if it's not big enough, you just stretch that. This is what you have to do. You can't take a screenshot of this. You have to do it yourself. And the second column, again, if you could stretch this as well, so it's big enough to say output voltage, and just put down here peak value. And again, I'll stretch it further. So that then you have those values 100, 500, and to have all the values in the center, I'll just highlight these two columns and centralize it by this. So it's whatever you write there is center. 500, 1000, 3000, 5000, 6000, 10,000. Sorry, I've just missed 8,000, 10,000, 20,000, 40,000, 80,000, and 100,000. So this is your values that's given in the question. Then what you have to do is just pick the values of the voltage from the circuit. You keep changing the value. I'll just show you how it is, but I'll just give you the numbers anyway. I'll just show you what I've done to get those numbers. So you explain that in your question. So you have put down 100 hertz, click OK on the value of the voltage and frequency, and then simulate that. Double click on the oscilloscope, you get this. That shows you, if I just, let me just put this a little bit further away and reduce the size of this a little bit. So I can double click on the oscilloscope. So now you really have two waveforms here, a red one and a blue one, but because they're on top of each other, you only see one. If I just increase the scale of one of them, the scale of channel A, you can see the same size, but because I'm just changing the scale to 5 volt per division, so each division is 5 volts. For the channel B is 10 volt per division. This is channel A, this is channel B. And this one is time per division. That is the vertical divisions. Sorry, the horizontal divisions. The voltage is vertical, the time is horizontal. Any one of these divisions, any squares, any square that you see on the screen is set, for instance, 5 milliseconds per division. And that's how you find the frequency of this. Anyway, so I move the traces here on top of the maximum, the peak of the value of the output, which is the blue one, and read it here. B, channel B, for instance, is 9.744 volts. And you keep doing this for different values of the frequency. So you keep going there. Change the frequency to, for instance, 500, and then 1,000, 3,000, 5,000, 6,000, and keep going up. So if I just jump to 10,000 just to show you how I've done it, and then simulate again, and you can see that obviously the frequencies changed. They are very tight, close to each other, so I have to decrease this time per division scale so you can see the waveforms better. You can see what's happened. The input is the red one, and now I can actually bring the scale of the voltage back to the same as the other one, because you can they're not on top of each other now. There is a shift in phase angle, so the capacitor has caused this phase angle shift. The input is behind the output. The output is leading input, or you can say the input is lagging output. Also, the voltage has gone down. You can see the peak of this red one is bigger than the blue one. So the output has gone down. Why? Because the frequency is increased. As you increase the frequency, because it's a low pass frequency, it allows the lower frequencies to go through, but as you increase the frequency, the higher frequencies are not allowed. So it just dampens this voltage, the blue one, down to almost zero. I can show you that if I just jump to a bigger frequency. Let's just say I jump to 30,000 instead of 10,000. Now you can see the blue one went further down, which is almost like if we just put if I just increase that, stretch it a little bit, so go with the traces. On top of the blue one, the maximum peak of the blue one is 4.6 volts, whereas I've given it 7 volts, so it's almost half a voltage. So it's not as effective as it used to be, or as it was to begin with. So it's almost getting to elimination of the output. Is the frequencies are getting eliminated, the higher range frequencies. That is the action, and that is the process of working. So I'm not going to do each one of these frequencies for you, but what I'm going to give you is the numbers that you need for that table. For each one of these values, I've got a range of numbers to give you. That is 14. You just accept, I'll accept these as 14.13. Next one, 14.11, 14.06, 13.76, 13.42, 13.21, 12.51, 11.93, 8.79, 5.31, 3.17, and for 100,000 hertz you get 0.415. Now the numbers you might get, if you actually build a circuit, you might get different values. It doesn't matter. What matters is if you just show, if you highlight these and go to insert, go on the charts, insert scatter X, Y, or bubble chart, and click on one of these types, whichever one you want. Right, this is your graph. So it's just going like this, and it's just basically crashing, at around here is really crashing, and that is where your cutoff frequency is. and that is almost, if this is 20,000, that's the middle of this is 10,000, that's over that. So it's about 16,000 hertz, where it's just suddenly crashing down and bringing the voltage at the output down. So this is how you compare it. This is how you see it on the graph, and also on this one. If I just close this Bode plotter is there to also show you the same thing but more accurate. So like I said, I've done this in a different video, but what I did in that video was I showed you with a black background. It wasn't very clear, so I just reverse it to white background so you can see this is the cutoff, this is the frequency. Basically, as long as it's flat, it means it's just carrying the input goes to the output with no problem. But when it's crashing here, that means after this, it doesn't allow the frequencies higher than this. So if this line, the horizontal line, is your frequency and this one is your decibel, the vertical line. So as you increase the frequencies, you get to the point that the decibel will crash, or the output signal will crash, and it won't allow more frequencies through. To find out where that cutoff frequency is, again, there is another tracker here. You pull this to a little bit further past that bend until you see almost 3 decibel, minus 3 decibel, as close as you can get to minus 3 decibel. So if I get to this one, this is the closest I think I can get to minus 3 decibel. This is minus 3.081 decibel. At this point, you record the frequency, which shows here 16.173 kilohertz, which is similar to what we calculated in our calculation. We said the cutoff frequency was 15,915 something hertz, which is 15 kilohertz, or almost 16 kilohertz. So our calculation showed that about 16 kilohertz. Our graph is showing this, which is about 15 kilohertz or 16 kilohertz, and also our Bode plotter is showing at minus 3 decibel. This is very important. You have to show that minus 3 decibel is 16.173 kilohertz. That is your cutoff frequency. If I go the next bit closer to 3 decibel, it would be minus 2.656, but I think that minus 3.081 is closest, so we just pick that, choose that one. Minus 3.081 decibel dB gives us 16.173 kilohertz. That is cutoff frequencies. Then all you have to do now is take a screenshot of this one as well and compare all these 3 results: calculation, Bode plotter, and the graphical result. And that's all you have to do. And for this part, obviously, you have to explain the operation of the low pass filter, read the question, and answer all those questions that's there. It's a distinction, so you need to answer as much in detail